looking at from the problem we're about to define, which is called the dual. And we define the Lagrangian to be this function. It's a function of the original variable x, that's the optimization variable, and then two other variables, u and v. And u has one component for every inequality constraint, and v has one component for every equality constraint. And we define it to be f of x, it's the criterion in the original problem, plus the sum of ui times the hi's, plus the sum of vj's times the lj's. Okay, so that's just some function of three variables, x, u, and v. This has the property that if x were feasible for this problem, the final problem, meaning that hi of x was less than or equal to 0 and lj of x equal to 0 for all I and j, and we took u to be non-negative in every component, then L of x u v is going to be smaller than or equal to f of x. Right? That's just because this guy is going to be 0, and this term is going to be less than or equal to 0. Okay, so it lower bounds our criterion function whenever u is non-negative in each component over the feasible set of our original problem. Okay, so that's why we constructed for that property. And if we want to take the tightest lower bound possible, then we just maximize over all such, or we can maximize over all points x. So what we did to get here was we had a sequence of steps. Maybe I'll write them down below here for you. We said that f star was bigger than or equal to, by construction, right, we're going to say this is equal to the minimum over all x in the feasible set C, I'll call it feasible set C, of f of x. But if I take any u that's non-negative in every component, then that's bigger than or equal to the minimum over all x in C of L of x u v. That's true by construction. And I said, well, this is certainly bigger than or equal to if I took the minimum unconstrained. That's probably why you had your hand raised. Is that right? No? Yeah, that was supposed to be the minimum. Sorry. I confused you. Okay, you can always minimize over a larger set and it just gets smaller. So we have f star is now bigger than or equal to unconstrained minimum for Lagrangian. And I just called this function, I defined this function here to be g of uv. Okay, so sorry that Max confused you there. That was just being mixed up what we're doing on the next step. So we just said that GUV provides a lower bound on the optimal criterion value whenever u is non-negative in every component. And that function g, which is a function now of u and v, we call it the dual variables, we call that the dual function. Did you have a question?
Yeah, so you said, so g is always concave and then we are going to optimize that. But how do you do that minimization? Like, because f isn't necessarily concave, right? Like, how do you do that minimization?
This one here?
Yeah, exactly.
Yeah, so that's not always easy. We'll go through examples of where it's possible, but it's not always easy. In fact, I have two examples. One where it's straightforward, one where it's very difficult. But remember, it's easy to minimize convex functions. It's easy to maximize convex. So, yeah, that's just one thing. Hey, Matt, I just told these guys that you would email out to the CMU like 10702 email list the homework, a PDF of the homework, because the stats website is down and someone don't have it.
Oh, okay. Yeah, I'll send that out.
Okay, great. All right. Okay, so it's a pretty kind of simple sequence of steps, but we get something pretty powerful by the end. Okay, and what we get is this lower bound, like I said, on the optimal criterion value. And if we want to get the tightest lower bound possible, we maximize over all arguments, u and v. but with the constraint that u has to be non-negative, right? Because you only get a lower bound if u is non-negative. That was the one kind of caveat. And that's called the dual problem. So that's this guy up here. I want to maximize the dual function, the lower bound on my primal criterion value, f star, overall possible dual points. So that's overall v and overall u that are non-negative every 2 points. The very first thing we get out of this is something called weak duality, which is that f star is always bigger than or equal to g star. So if I call g star the optimal value of that problem and f star the optimal value of this problem, we always have this relationship by construction. This comes from here, right? And f star is always bigger than or equal to the dual function. So I get by maximizing over all dual points g star. So I just get this inequality there.
Shouldn't be the first two mean, I mean the mean of address and the shouldn't be that inequality equality?
This one? No.
Because this is divisible and isn't that?
No, because if x, let's suppose I took u to be strictly positive at this point. If x is feasible, then hi of x could be less than 0 strictly. And so I get that this whole thing is strictly less than 0. So generically, no. Okay, but the kind of trick, if we did any trick, which we didn't really do at all, but the only really clever thing we did is that we decided to minimize unconstrained Lagrange rather than constrained, because we knew it would still give us a lower bound. So, is it Robert? Did I get your name wrong? What was your name?
AJ?
Sorry, AJ. I don't know why I said Robert. AJ asked the question, how do we do this minimization? Well, it's even harder if we have this constraint here. Okay, so if we decided to define the dual problem like this, or the dual function like this, then I could give you essentially no examples where we could try it. So yes, this is not always easy, but it's definitely easier than this problem, this constraint problem. Okay, but weak duality is on the end of the story. The real punchline is that we often get what we call strong duality. And that's a situation in which we actually have that f star is equal to g star. And more than this, even more so, we can get x star from u star, p star. So if I have dual solutions, I can actually get a final. Now, this definition of strong duality is this. It's that the lower bounds is equal to, the best lower bound we construct from duality is equal to the optimal function, primal function value. It's not this. This is just often what happens under strong duality. Okay, so we can have a situation in which we have strong duality, but it still is pretty hard to get a final solution from dual solutions. It's just that often this happens. And we'll kind of be clear about that when I give you examples. This is really, I'd say, the most useful part of duality. It's getting a primal solution from dual solutions. Okay. So I'm going to give you some examples. I think it'll help clarify things. First, I'm just going to show you in a couple lines why the dual function is always concave. And once we know that, it means that problem is always convex. Right? Because if the dual function is concave, in the dual problem, I maximize it subject to a linear constraint on u. So that is a convex problem. Maximizing a concave function subject to linear constraints. I can write that as minimizing a convex function, right? Minimize minus g. But with those same constraints, it now becomes a convex optimization problem. So why is the dual function concave? Well, let's just take a second to stare at it. it's the, by definition, it's the minimum over all x, right, unconstrained, of L x u v. Well, what's that? It's f of x plus the sum of ui hi of x plus the sum of dj lj x. Right, I'm going to write that as negative maximum of all these quantities, of the negative of these quantities. Did it change anything? And now I'm going to look at the inside. So as a function of u and v, what kind of function is that? Yeah, it's just a linear function. Or I mean, I would say an affine function, but it's the same thing, right? Because of that, it's just the opposite. Affine function or linear function, depending on the terminology you favor, in UV. But affine functions are convex, right? So this is definitely a convex function in U and V. So what happens if I take a maximum of convex functions, pointwise maximum, right? This guy at a point UV is just the maximum of a bunch of convex functions in UV. It's convex, right? So it means that this whole thing, this up to this maximum, this is just a single convex function. One of our rules that taking pointwise maxima of convex functions gives you a convex function. And look, I have g as a minus convex function, so g is concave. Right? It seems like almost like we're cheating. It's so simple, but that's the argument to show that g is concave. Okay, so that was true. It doesn't matter what f and h and l are. G is concave, so no matter how ugly and non-convex the primal problem is, the dual problem is always going to be a convex problem. So I'm going to give you two examples real quick. And we're going to observe that in one example we have strong duality, and the other we don't.
So you're right?
Yeah.
So after you maximize, it's no longer going to be affine and U and V, but it will still be convex.
Correct. We don't know that a maximum of affine functions, pointwise maximum, is going to be affine. In fact, it'll be like piecewise affine, right? Like piecewise limit, but it'll still be convex. Okay. So I'm going to start off with a simple example where we do get strong duality, and it's going to be something that we call a quadratic program, a QT. So all this means is that I'm going to be minimizing a quadratic function. X transpose QX plus C transpose X. So when is that a convex function, by the way? Is that always a convex function? What's that? Right, I have to know that Q is positive semi-definite. And here I'm actually going to make it strictly positive definite for simplicity. Although that may not be the case, but it just makes the calculation easier. Subject to, I'm going to put some constraints. Ax equals b, and x being greater than or equal to 0. Okay, so how do I form the dual? Well, the first thing is I take the Lagrangian, L of x v b, and I take the function, the criterion function, which is a half x transpose qx plus c transpose x, and then I do plus the sum of ui times the inequality constraints. Well, here and inequality constraints up there were in the form hi of x are less than or equal to 0. So I'm going to just write this as minus x less than or equal to 0. So each of my inequality functions just gives me a component of x, like hi of x is minus xi. So that becomes u transpose x, or minus u transpose x, right? That's the sum of hi times dy. And then I have, I can write this as ax minus b equals 0, right? And my equality constraints look like this. So that's Lagrangian, and remember its domain is u bigger than or equal to 0. Otherwise, this would give us a lower bound on this with a feasible set. And what's g? G is the minimum of this over all x. So how do we minimize this over x? Let's just group the terms that depend on x. Minimum over all x of, I get 1/2 x transpose qx. What's the linear term look like? I think I want to write it as minus, no, I guess I'll just keep it like this. C minus u plus a transpose b transpose x. And then I still have this term here, minus b transpose b. So whatever I do to compute this part, the dual function is going to at least have this term minus b transpose b. And that's always going to be in the dual criterion value. And how do I get this? Where do I go from there? Well, that's just a quadratic, right? So unlike the primal problem, which had constraints, there's no constraints here. It's actually very straightforward to get the minimum here. I can differentiate and set it equal to 0, and I know how to get the minimum. And so if you do that, and by the way, one thing I always remind myself is that for a quadratic in one dimension, right, if the quadratic looks like this, its minimizer, this is trivial stuff, but I always remind myself its minimizer is minus b over 2a, right? I just remember that, so then if I have in general, if I have a quadratic form like that, its minimizer is going to be the same thing, but a is a matrix, so I have to take the inverse of that. So for a matrix, it's just minus a inverse b over 2. Right, so the minimizer here is just minus q inverse times that. Okay, so when I plug that in, I get this expression, minus 1/2 c minus u plus a transpose b, q inverse c minus u plus a transpose b, and I still have this guy, minus b transpose b. So that's the dual function. And though it may not be apparent by looking at it, if I give you any u and v where u is non-negative for every component, if you evaluate this, it's always going to be smaller than or equal to the optimum value of that problem. Okay, we know that by construction, but then when we start it here, it's not so apparent anymore, but that's what we know by construction. Okay, so what's the dual problem? The dual problem is just going to be, I'll just skip ahead and say the dual problem then is to maximize this over all u that's non-negative. And b, right, sorry. There's no constraint on b. Okay, now if you were to play around with this, if you plot examples, you would see that whenever I do this, I always have the optimal value of this problem equals the optimal value of that problem. So I always get strong duality no matter the example I try, as long as Q is positive definite. In other words, if I were to somehow plot the optimal, or so the primal criterion quadratic over its domain, and I were to plot the dual quadratic over its domain, I'm going to get that they touch. The minimum of this one is equal to the maximum of this one. And they have to obey their ordering that the primal criterion is always above the dual criterion, but they're going to touch it off and on. So I do get strong duality. Okay, and I have an example in the notes of where that happens, so you can see the picture. Okay, so that's one example we get strong duality. We'll come back to that in just a second. Here's another example in which we don't get strong duality. Okay, this one is one-dimensional minimization problem. Subject to okay, is that a convex problem? Or when is that a convex problem? I guess it's hard to say with this constraint, so forget about the constraint. Is that a convex problem? It's not, right? Because of this guy. It can't be. And so if you plot this function, you're going to see it looks like this. The reason I said it's hard to tell what happens with the constraint is that it could be that the constraint lies here and has the feasible region the function is actually convex. So it's hard to intuit what's going to happen with this guy. But what happens if you plot it, the constraint comes into play like right here. Okay, so that's the line x equals minus 4.5. So I've chosen a non-convex optimization problem. We're trying to minimize this over this constraint set to minimize this function. The minimizer is going to occur at x equals minus 4.5. It may seem simple, but because the minimizer does occur here, but actually it's an interesting problem with respect to duality. So how do I derive the dual function here? I just form the Lagrangian like I usually do. Okay, L of x u v. But here I actually only have an inequality constraint. I don't have an equality constraint, so it's just L of x and u. So I only have one dual variable. And that's equal to the minimum over all x. I'm sorry, Lagrangian isn't. Lagrangian is just x to the fourth minus 50 x squared plus 100x. And I do minus, or I say plus u times 4.5 minus x. That's not right. X minus 4.5. Okay, because I want to have the constraint not. Neither of those are right. Okay, so I want to have the constraint in the form something is less than or equal to 0, and so it looks like minus x minus 4.5 less than or equal to 0. So I'm going to multiply that by the equal. So why I chose this example, I had to think carefully about a couple examples of non-convex problems that I could actually do the minimization. Because, as AJ asked, not Robert, this is usually not easy to do when the problem is non-convex. But this one I can do even though it's non-convex. And that's because it's a quartic function, and so its extremes are going to be the roots of a cubic equation. The roots of cubic equations have explicit solutions. They're very messy, but there are explicit solutions. People did this hundreds of years ago. They were interested in roots of cubic equations. And so I chose this example because I could actually drive the dual function exactly through this problem. Okay, and so here it is. I'm just going to write it for you. I'm not going to go through the derivation. It's not insightful at all, but be assured that you could do it just by one-dimensional algebra, basically. It's the minimum over a set of pointwise minimum over 3 functions. Those functions I'm going to write as fi to the 4u minus 50 fi squared of u plus 100 fi of u, where fi is this function. I don't even know why I'm writing this. It's going to get really complicated, but I didn't want to show you one punchline. So that's the function. Where AI is equal to 1, A1 is 1, A2 is minus 1 plus I over root 3, and A3 is minus 1. Sorry, this is 2. Okay, so that's the dual function. It looks pretty dense, but let me ask you a question now. Is that concave? It must be, right? Because the dual function is always concave. I would pay anybody in this room a large sum of money if they could derive from first principles that this was concave. Actually, I'm not going to offer that bet because I might lose. But it's not easy to see this is concave if you look at this function. It's very difficult. I don't know if you saw, this is 1 over this to the 1/3. So I have polynomials nested with another polynomials in the denominator and the numerator. It's not at all always a concave function. Then I take, not only that, I raise that function to the 4th, subtract off that function squared, and add that function. There's just many, many transformations on top of each other, but it's concave. So one way to prove that something is a concave or a convex function is just to say, hey, it's the dual function of something I know. Doesn't matter where it came from. Okay, so now what I do with this problem is, I didn't know whether strong duality helped. I probably guessed it didn't, so I just tried it. I numerically maximized this function. Overall, you get it positive. And I just saw whether it gave me anything close to the minimum of my criterion value at that line. And this is what it looked like. So here's the dual function as a function of u. And u has to be positive, so that's 0. And here's a horizontal line that denotes the minimum of that convex function, that non-convex function there. So it comes down at this touches here at 4.5. It looks like this. Okay, so there's what we call a duality gap here. I don't get strong duality. There's actually a non-zero gap between the maximum of the dual function and the minimum of the primal criteria. Okay, so why does this happen? Well, there's kind of a rule here that we should remember, which is that pretty much almost every time when you're doing a convex optimization problem, you will get strong duality. And we'll make that precise in a second. But pretty much every convex optimization problem admits a strongly dual optimization problem. So this dual is going to have a property that they match optimally. That's not true with non-convex problems. In fact, with non-convex problems, you're more in that kind of pick and choose scenario. I can tell you a non-convex problem where we get strong duality. I can tell you many, many more where we don't. Question? It does not, no. It does not. What's that? No, because this maximum is over an infinite number of points. But if this maximum over x were like over a finite number of points, then yeah, it would be piecewise. But actually, an interesting point is that it looks piecewise out. And that if I had to make a non-rigorous claim, that happens a lot of times when you look at dual functions of non-convex criterion values, that they tend to look piecewise out. If you look very carefully, this is curved. It is this function. It's not piecewise out, but the first approximation looks close to it. Okay, I'm just going to write down now the most general condition that we know of under which strong duality holds. And that's called Slater's condition. Actually not the strongest one, or not the most broad one, but it's the one that's easiest to remember. And it's as follows. If the primal is convex, and strictly feasible, then we get strong duality. What does strictly feasible mean? It means that we just have to have the property that there exists an x, there is some x that need to be optimal. There's just some value of x such that h9 of x is less than 0 for all of our inequality constraints. Okay. Yeah.
So is that not necessarily just the function f, but the set of feasible x's is convex? Like if in your ugly problem there with the four-digit function, if the constraint on x weren't negative 4.5 any further to the right, then the dual would give you a type now.
No, I don't think so. That's a very good question, actually. So to repeat the question, if people didn't quite catch it, Jersey asked, what if I made the constraint here? So that to the right of it, the function was convex on the feasible set. That doesn't meet Slater's condition, first of all, because Slater's condition says that the function is convex. And there's a strictly feasible point. Although I guess we could have redefined our criterion function to be one that was identically equal to this guy, say for x bigger than, maybe this was positive 4.5, and infinity outside of it, and that may have been convex. Yeah, I'll have to get back to that. I don't really answer that question. But whether you can take a non-convex problem and you call this make an extended value, like I would just call it to be infinity outside of the constraint region. I think we would get strong duality here actually, in that example. I'd have to try it, do that. Okay, but the general condition is that the problem has to be, the final problem is convex, meaning that the criterion function is convex, the inequality functions are convex, and the equality functions are affine, and it's strictly feasible. So that's why I said almost every convex problem. You rarely encounter a convex problem whose inequality constraint set is not strictly feasible. And that would be a pretty odd convex problem. They exist, but generically you encounter problems that have this property. I can find an x, at least one x, that makes the inequality constraints not tight. Okay, the very last thing I'll point out about duality, and then we'll move on to KPT conditions and sparsity, is the concept of duality gap. And this is a very useful concept for many reasons, both algorithmically and theoretically. But if we have a feasible point x and a dual feasible pair, u and v, so this just means that u is non-negative, right, and v is anything, then the quantity f of x minus guv is called the duality gap. So first of all, this is always non-negative, right? Because f of x is always going to be bigger than or equal to guv. That's certainly true. Because if I minimize this and I maximize that, I still get something where f star is bigger than or equal to g star. But moreover, if I know that, say the duality gap is less than or equal to some number epsilon, that actually tells me that the primal, the gap between where I am with x and where I would be at optimal is less than or equal to epsilon. And that's because we have this kind of obvious relationship. Okay, f star is always bigger than or equal to this guy. So the gap between f of x and f star is always less than or equal to the gap between f of x and g. It looks like this kind of, right? This is my primal function. Say, even if I didn't have strong duality, but my dual function, maybe I'm here, and I'm at a dual point where I'm here. This is x, and maybe this is indexing uv. Just telling me that this gap is always bigger than or equal to the distance between how big I am to optimal. This would be f star. And we have the same, we also have the bound that, although this one's used less often, right? I also know that g star minus guv is also less than or equal to f of x minus guv. Right, so I also, it's just this gap right here. The gap between the dual optimal value and wherever I am is less than or equal to the duality gap. So, what's one conclusion that we get from this? One conclusion we get from this is that if the gap is 0, that implies that x is optimal, right? X is a primal solution, and uv are dual solutions. Why? It's very simple, right? Because if the gap is 0, that means that this guy has to be 0 too. So that means that I've achieved the optimum value. And that means this guy has to be 0 also. So again, I've achieved the optimum value. Okay, so that's actually the launching point for the KKT conditions, is this duality gap notion. When the duality gap is 0, it implies that we have the solutions. And let's take a quick break and we'll get back to that. Well, actually, I should say before, I don't have a joke for you guys. I'm sorry, that's why I told that joke at the start. If somebody has a joke, they're welcome to offer it. All right, well, we'll count it as a joke. Oh, sure, yeah. This is Larry's idea, it's not my idea. So my dad, who's a statistician, and one of his colleagues are starting a blog. Larry thinks it has a terrible name. I think that the blog's proposed name is weak also. The proposed name of the blog is Statistical Yearning. And so Larry's idea was to hold a contest as to whether someone in this class could come with a better name for a blog than Statistical Yearning. And you'll get, I don't know, something, right? Pizza or something.
There's some sort of box.
Some sort of
What's the topic of the book?
Statistical learning is the topic. Yeah. Yeah, I know. It was a weak name. There was no laughter.
What's the current
Even
statistical
weaker than my-
learning? Is that the
even weaker than my
word?
joke on,
What's the name?
Yearning.
Okay, here are the KKT conditions. This is a nice thing we get kind of right from duality. I think of them as, like I said, intimately linked to duality. And actually, I don't think we're going to do this because we are short on time, but you can prove these from duality. The arguments are about maybe 4 lines in each direction. But what do I mean by them in the first place? I have the problem. My problem, minimize f of x subject to hi of x less than equal to 0. I'll do x equal to 0 for my standard problem form. Again, I'm not going to assume it's convex for now. I'm just going to say it's an optimization problem. Associated to that problem are something called the KKT conditions. There are a set of conditions on x and 2 other variables u and v. Think of those like dual variables. And there are 4 conditions. The first is that if I take a subgradient of f of x and I add to it a subgradient of hi times ui and sum those up, and I add to a subgradient of lj times bj and sum those up, I have to be able to get 0. What is this function in the middle here, this guy in the inside? That's the subgradient of the Lagrangian, right? If I take the subgradient of the Lagrangian with respect to x, and I treat u and v as constants, all this is saying is that 0 has to be a subgradient of the Lagrangian. What does it mean for 0 to be the subgradient of a function? It means that function is minimized at that point. Right? We learned that when we learned about subgradients. If 0 is subgradient of f of x, it means that x is minimized at that. So this is saying that at the point uv, x has to minimize the Lagrangian. Okay, so all of a sudden, this is sounding very close to duality. I'm just saying that if you give me u and v, x has to achieve the minimum value of the Lagrangian. This guy is called complementary slackness, the next condition. These are really only the 2 conditions that may be something surprising to you. But they're not totally obvious. This is called stationary, this is called complementary slackness. This says that I have to have either ui being equal to 0 or hi being equal to 0 for every I. I can't have them both being loose. Remember that if u is a dual variable, then it should be bigger than or equal to 0. It's saying that I can't have ui being positive and hi being negative, strictly for both of them. You have to have at least one of those 2 inequalities being type. And then the last 2 are conditions that, of course, you would no have to hold, right? I have to have that x is feasible for the primal problem, and u has to be negative. It's called dual feasibility. So these are a set of 4 conditions. I haven't told you what happens, what the relationship is to the problem, but here's the relationship. The KKT conditions are, let's see how I wrote this down. So they're always sufficient, which means that if I told you that I had x, u, and v that satisfy these 4 conditions, that always implies that x is the solution to this problem, and u and v are dual solutions. That's true whether or not the problem is convex. That's always true. So as long as you can satisfy the KKT conditions, you can find solutions. Primal solution and then a pair of dual solutions to go along with it. And they are necessary under strong duality. So if we had a problem where strong duality held, convex or not, they're sufficient and necessary. So let's suppose we're in our usual framework now where we're doing convex optimization, and the problem is strictly feasible, so we know that strong duality holds. That's most often the case that you'll be working in. And the KKT conditions are equivalent to optimality. They're necessary and sufficient. So if I satisfy them, I have primal solution and dual solutions. If they're satisfied, if I have primal dual solutions, then they have to be satisfied. I'm not going to prove this, like I said, because we're short on time, but the proof in each direction is like 3 or 4 lines, and it's in the notes, so make sure to go through it if you're curious. It just uses a couple arguments from duality. That's all it is. This is a duality gap. So let me just talk you through how it's shown. In this direction, sufficiency, we just showed that if we have this, then the duality gap is 0. It's actually very easy to prove that. It's like 3 or 4 lines. If the duality gap is 0, then x and u, v have to be solutions. X is common solution, u, v dual solution. Okay. In this direction, we basically just use the fact that if we have a zero dual gap, which we know happens under strong duality, right? If we have solutions, and we have a zero dual gap, which happens under strong duality, then all this stuff falls out. Well, this is certainly going to fall out. If they're solutions, these two definitely have to hold. And the fact that this falls out just comes from looking at how we define the dual component. You'll see immediately that we have to have the property that x minimizes Lagrangian, and its complementary slackness criterion also met. Okay, one word of warning before we move on from the KKT conditions and do like an example, and then maybe a very short sparsity example, is that people often forget that this is a subgradient, and they say, oh yeah, okay, KKT conditions are always sufficient. I have my favorite problem. Doesn't matter whether it's convex or not. It's always sufficient. So I'm going to try to satisfy the KKT conditions. And, oh, I did, and I have a solution. But what they do sometimes is that they forget that this is a subgradient. This is not a gradient. So let's suppose I had f, h, and l all being smooth functions. So they are smooth. They have gradients. Let's suppose that they were non-convex. That doesn't mean that their subgradients are just their gradients. Remember? For a non-convex function, I could have the property that doesn't have subgradients. Like this function. Right? It does not have a subgradient of 0. So if I have a smooth problem, I'm saying we cannot replace this with just gradients here. When can we replace them with gradients? Well, if they're convex and smooth, then I can think of stationarity as just the gradient condition. but not when they're non-convex. The subgradients and gradients are not the same. So it's often a mistake I think people use, and then they try to employ the KKT conditions, and they get us something that's not a solution. Yeah.
See, the problem is not convex, but you do find subgradients which satisfy this condition, then you have your solution.
Correct. So the problem is not convexity so much as that if you're going to be making the automatic transfer in your mind of smooth means that I have a subgradient unique to this. If you have a non-convex problem and you manage to find subgradients and you manage to prove that 0 is subgradient, then you're fine. But if it happens that subgradients don't exist, right, this set could be empty, in which case you cannot satisfy the solution. Well, we're pretty much at time, so I guess I'll just maybe say one more thing. No, is that right?
We got time.
That clock's not right. Oh, we have lots of time. That's why I borrowed Larry's phone, because that clock's fine. Great. Okay, well then I'm going to be able to go through some good examples, and we'll make our way to this question. Okay, so we're going to do an example using the L1 norm, which is where we're heading next. But there are other examples in the notes about KKT conditions with other problems. There's some other things that might be important there to read if you're planning to use these in a generic context. Okay, so I'm going to look at the KKT conditions just for the lasso problem, lasso regression problem, and then we're going to give like lots more motivation inside about the lasso whenever we get to that sparsity unit. So let's suppose we're in a regression setting where I have some outcome vector y, and I have some matrix x of predictors. So I'll think of this as, this is an n-dimensional vector. This is an n by p matrix of predictors, and each column is going to be the measurements of a different predictor, or feature, or variable, whatever your favorite notation is, or nomenclature is for that. Okay, so usual least squares regression minimizes the least squares criterion by overall choice of coefficient vectors. We're going to talk about next time, or not maybe even this time, depending on how far we get, some theory and motivation for this modification of the problem. But we call this lasso regression. So it's a penalized version of least squares. And just to remind you, the L1 norm is the sum of the absolute values of the components of the coefficient vector. Okay, so this coefficient vector beta is p-dimensional. All right. Let's suppose we wanted to do the KKT conditions for this guy. Well, actually, in this case, there are no constraints, right? So what happens when there's no constraints? Well, you don't have any dual variables. Right? You have nothing. All these don't mean anything. All we have is that 0 is in the subgradient of f of x. That's necessary and sufficient for optimality. A convex problem, it is strictly feasible. There are no constraints, so that's fine. So Necessary and sufficient for optimality is just that 0 being the subgradient of this criterion. Well, we actually already knew that. That was just called subgradient optimality. Right? So in this case, the KKT conditions are a little bit of overkill, but I'll call the KKT conditions anyways this subgradient optimality. So let's just take the subgradient of this criterion. I'm going to take the gradient of this and add it to the subgradient of that. The gradient of this term is just minus x transpose y minus x beta. Right? By the chain rule. And how about the subgradient of the one norm? Well, I'm going to call that lambda times s. And I'll just say that s has to be the subgradient of the one norm of beta. And for beta to be optimal, I have to have this be equal to 0. That's all that the KKT conditions say. Right? Again, if we call this f of beta, all we're saying here is that 0 has to be the subgradient of f of beta. So that's all those used. All right, what is s more explicitly? S is equal to, it's going to be equal to plus 1 if beta j is bigger than 0. Not just calling what the subgradient of the one norm was. We did this back when subgradients. It's got to be equal to minus 1 if beta j is less than 0, and otherwise it's got to be in the interval minus 1. Okay, so it's the sine of beta if it's non-zero, otherwise it's in between minus 1 and 1. So if I rearrange this, it tells me that x transpose y minus x beta has to be equal to lambda times s. So if I can find a vector beta that satisfies this, I have a Lasso solution. Where s satisfies this. It's the sine of beta when it's non-zero. Otherwise, it's anything between minus 1 and 1. Now, I can't find this analytically. If I could, then a whole bunch of literature on computing the Lasso solution would be useless, but we can't find, there's not an analytic solution to this that we know of. But I can read off actually a bunch of really interesting and helpful facts just from the KKT conditions. And that we'll do in like pretty good detail when we start talking about theoretical properties of the Lasso. They all come from the KKT conditions. Everything does. Pretty much, except for kind of one very basic thing. So let's just begin now. What happens if I have the property that at the solution, so suppose at the solution I have xj transpose y minus x beta in absolute value being less than lambda, strictly. What does that tell me about the Lasso solution? And what does that tell me about Sj? So this is I can write this as xj transpose y minus x beta equals lambda Sj for j equals 1 through p. I'm just equating each of the j components of these two vectors. So what happens if I tell you that the inner product of some feature vector with the Lasso residual is strictly smaller than lambda? What does that imply about the subgradient? Like the jth component.
X is at 1 minus 1, so beta j.
Right. This tells me that beta j equals 0 at the solution. So if a variable like xj doesn't achieve the maximal correlation with the residual, the maximal correlation being lambda, right, because s can't be bigger than 1 in absolute value, then automatically it tells us that at the solution beta j is 0. This automatically gives us an idea of why the L1 norm gives us sparsity. So anytime we have this property solution, it means that we're setting variables to 0. How about the other direction? If beta j is 0, do I have this property? Not necessarily, right? Because if beta j is 0, it could be the case that I still choose the subgradient equal to minus 1. Okay. Let me just jump right into to sparsity then. Are there any other questions about the KKT conditions before we kind of leave them generally, go into the specifics of sparsity? Right, so if you're having trouble with the idea of the KKT conditions and duality beyond kind of definitions, go through the lecture notes. You'll see lots of examples of both deriving in different scenarios. You'll see, I think it just helps to work through them. Deriving duals and verifying KKT conditions and so on and so forth. And we're going to come back to duality for the lasso, and you'll see it in action. I'll actually show you how we get from the lasso dual, like a lasso solution, and we'll see like how they all connect and stuff like that. So that'll be a good example of the use of duality in the KKT conditions. Okay, so I'm going to do our start on sparsity now. I have about 7 minutes left. How many people have learned the lasso and rate regression and all that stuff in another class? How many people are very comfortable with the notion of regularization, or let's say pretty comfortable, and do not need to hear like a general explanation of why we regularize maximizing the problems for these squares? How many people would find that helpful if we did go through that? Okay, so I'll do a little bit, just because a mix of hands. The first 3 pages of these notes, which you can't look at because the stat server's down, so when you can look at them, they do go through this in pretty good detail. So you'll be able to like read that if you're uncertain of the concept of regularization. But let me just start off with very quickly some basics, and we're going to just work in the least square setting. A lot of it we talk about transfers over to maximum likelihood, and we will make statements about maximum likelihood, theoretical statements under L1 panels and stuff like that. So this is just a start. But yeah, we'll be in the least square setting, and so this is just generic least square expression for now. So I suppose I have y and x like I had before, outcomes and predictors. And one of the problems that we encounter is that if rank x is less than p, so suppose x is n by p, the moment that x has columns that are linearly dependent, right, so there's p columns, and so if the rank of x is less than p, means it's linearly dependent columns, then we'll call this f of beta. F is not strictly convex. So and that's one way to say it, having some convexity. Why is that true? Well, remember, this is differentiable. It's twice differentiable for that matter. Its Hessian is x transpose x. Actually, I shouldn't go that way because that's not necessary. Let's just say that if rank x is less than p, right, and you claim to have a solution beta hat, then this criterion is going to be flat along any directions that look like beta hat plus c times eta, where eta is in the null space of x. Okay, so if x has linearly dependent columns, there's going to be some vector eta when I multiply that has a property that x times eta is 0, that's in the null space of x. And so that if I have a solution beta hat, this is also a solution for any number c. Okay, so we just argued directly that the solution to the least squares problem is not unique. And, well, for example, if that happens if p is bigger than n, then this is the case. Right, we can't have p bigger than n and have rank x equals p, because x is an n by p matrix, so its columns must be linearly independent. And why is this a problem? Well, so why can't we just deal with all those solutions? Well, here's one reason why we can't deal with them. If this is the set of solutions to this problem, right? You give me one solution, and I can generate other solutions non-uniquely by just adding elements of the null space of x. Then there is going to exist two solutions. We'll call them beta hat and beta tilde, such that beta j is bigger than 0, but beta tilde j is less than 0 for some j. Right? Why is that the case? Well, let's suppose beta hat was a solution. Then I know that if I add any element of null space of x to beta, that's a solution. And eta is not going to be, I know that eta, there is a choice of eta that's not all 0, because the null space is not trivial, because the columns are linearly independent. Features are linearly independent. So there's going to be some component of eta that is non-zero. Let's say that's the jth component. Then I can just, if beta j is positive, I can just add bigger and bigger and bigger multiples of eta in the right direction to make another solution beta tilde whose jth component is negative. So this is disastrous from the perspective of interpretation, right? You compute one least square solution to say that the partial effect on y is positive, here its partial effect is negative. That's not at all okay for the purpose of interpretation. So how do we get around this? Well, we apply regularization. That's the one way to get around this. And all we do is we're going to say we're going to minimize this least squares criterion subject to some constraint on beta. Like we'll say beta has to lie in some set C. Now the choice of this constraint is going to affect the quality of the solution. Depending on the situation, you might want to use a different constraint versus another. But we're going to want it to have a few properties. One is that either it makes the solution unique, or if the solution is not unique, it better not have this problem. It better have a more well-behaved solution. And we're going to want other things too, like it should have increased accuracy when we regularize. Maybe it should help with interpretation. If p is really large, you might want something like sparsity, where the solution would set a bunch of the components of beta to 0. And that's where the L1 norm comes in. It's a specific choice of regularizer. It gives us both increased accuracy in a lot of situations, and it gives us, it aids in our interpretation because it's going to set a lot of the components of beta to 0 at the solution. So it's just one choice of a set C, and we're going to constrain beta to lie in a set of all vectors whose one norm is smaller than or equal to some parameter. And that gives us the lasso problem. And so the notes I have some comparisons from the last one with the ridge regression, which just chooses a different norm here, 2 norm. So you can read that for a refresher, what the differences are, but we're going to stick with the lasso because it gives us sparsity. That's really the winning property of the lasso. So why is sparsity important? Well, sparsity is helpful because if we set some component of beta to 0, that means that we're basically saying there was no point in including it in the linear model. There's no explanatory power, right, in predicting one. Because the coefficient of xj was 0, so it's like I didn't have that feature in my regression. In other words, it's community variable selection. Okay, so that was just kind of like a very brief overview of regularization. I guess that's all the time we have. So enjoy Spring Carnival. On Monday, we're going to prove a bunch of theoretical properties of this guy, and I'll try to convince you it's a good idea.